Okay? By itself, it's at equilibrium. Yeah. Then we have the spring compressed certain distance d by a stone of mass m, right? So in this is the equation you use. In this particular case, we're going to say it's KD because that's what we're dealing with. Now, real quick sum up of springs, just for your benefit, I'm going to address it, the whole chapter, in about a minute. Got a spring. We got 3 different scenarios. Should have done it there. Alright, so we got 3 different scenarios. Where it's at equilibrium, 0, where it's compressed, this is 0, this is D again, and then where it's stretched, this is 0, this is D again. Okay? So now why they say F is equal to negative Kx is because, or negative Kd, because I use D again. This is the natural state of the spring. It wants to stay like this. It has a certain number of coils, and how thick the coils are, slash how many coils there are, slash what material, if it's steel, rubber, plastic like a slinky, whatever. All of those things affect this K. How strong the spring is. That's what affects the K, okay? And it maintains, it's the same, that like this spring has this K always, unless you suddenly mess with the metal in it or how many springs there are or whatever, which is not going to happen. Okay? So you deal with spring, it's going to have the same K. It's a property of it. Now, why it's negative Kx is because usually they deal with stretching the spring first. They stretch the spring because they deal with scales. This is what they usually use springs for. That's why they say negative Kx, because they stretch the force, or they stretch the spring, and so the force of the spring is going in the negative direction. Okay? It's going in the negative direction, and so that's why they have that negative Kx to make it a positive force to cancel it out, because they always are generally stretching the spring and it wants to come back to where it was. Can you see? No? There are seats back there. There are empty new seats. Oh, okay. Anyways, so that's why they deal with negative, and when they push it, they compress it, then all of a sudden it's in a negative x direction. This is a negative d, or a negative x direction. So then it's double negative, and it still ends up with a positive force. That's why that negative kx is there, that negative. So that's just semantics, really. So just forget about it. It's in the book, but now you understand why they have it there. It's just semantics. So don't worry about it. You know which way the spring is going, because you can see it. That's all you need. Anyways. So for this equation, or for this problem, we have a stone going on this spring. Let's make it touch. Okay. And it has force of gravity, mg, right? And it's at equilibrium now because it's not moving anymore. It's not bouncing up and down. It's not oscillating at all. And so therefore, F net is 0. That means the force that the spring is, and the spring's wanting to push back up, right? It wants to get back to equilibrium, right? So the force that the spring is pushing back up, Fs, is exactly equal to mg. And in this case, Fs is equal to kd, right? The force of the spring constant, or force is equal to the spring constant times the distance that has changed. So that means mg is equal to kd. We're looking for k. All we do is bring it over here. K is equal to mg over d. If you draw this question out, or any question like this, try this.